if we have to divide any kind of deforming material in a conventional weld or dissimilar weld, then we can divide it into two categories. One will be overmatching, another will be undermatching. And so the definition is, if the whatever, so weld zone or heat affected zone or any other zone, if that has a yield strength more than the matrix material, we call it overmatching, less undermatching. And so some work was done previously to understand how it influences the crack tip when you have a jump in a differently deforming cases. And a lot of work has been done on room temperature. Recent work has been done also at elevated temperature when the material is deforming under heat. And this presentation should work as a prologue to that. And if you are interested how this happens in creep, then you should watch my presentation on the third day. So this is just a trailer for that. So previous study has shown that you can have material changes. So in the reference configuration, you can have changes in the elastic modulus. So for example, if you have on one side steel and on another side titanium or something, which has a very drastic change in elastic modulus. The other change could be that the elastic modulus is same but the yield strength is different. And the third one could be a combination of these. Of course, the strain hardening coefficient, if that has a change, that will also increase. So in this graph, what you see is the normalized crack driving force or the pseudo elastic energy release rate in terms of J integral from Rice. And we calculate it via a different route, which is by the application of config forces, which I will try to explain in a bit. So on y-axis, you have normalized crack driving force. And on x-axis, you have a normalized distance from the interface. So the blue dotted line, which are vertical, they are presenting the interlayer. And this interlayer is different from the matrix material. So it can be a weld zone, for instance. And so what is happening at the first interface, if the weld zone is overmatching, then the crack is transitioning from a normal yield strength to an overmatching material. So you can say that it is transitioning from a compliant material to a stiffer material. And at the second interface, reverse phenomena is happening. So if you have only two materials and one interface, then that effect will be different. If you have an interlayer, so you have another material behind it, then you will have a reverse phenomena happening. And so in this case, using configurational forces, the effect has been calculated. And you see that linear elastic calculation shows a different, so let me explain this. J integral is path independent, and we'll talk about that. So if it was path independent, and that would be the case if it was homogeneous material. If it is a homogeneous material, then it will be a horizontal line at 1. So J tip will be equal to J far, because that will be path independent. But in presence of a different material, what is happening? So each point on this plot is one model at different crack tip location. The same result can be obtained, but if you incorporate a damage model in finite element analysis. So what happens is, when the crack comes closer to the first interface, the crack driving force is increasing. That means that crack is getting attracted towards the first interface. That means that for the same amount of energy which you have supplied to the specimen or to the component, the crack will have a tendency to grow faster and to come closer to the interface. And reverse will happen when the first interface is crossed, so it is broken, and it faces the second interface where reverse transition is happening. So it is going from stiffer to a compliant material, so high yield strength to low yield strength material. And in that case, the crack driving force drops down in the interface, and that's the interesting point. So the scenario will be reversed. So for example, if I have steel in the matrix and in the interlayer is aluminum, then this will be the case. But if I have aluminum in the matrix, which has lower Young's modulus or yield strength, then the plots will be different. And the interesting point is where the crack driving force drops down. If it drops down lower than the resistance offered by the material, then you can stop the crack. So you can use this phenomena to arrest the crack without changing, without doing heat treatment, without doing anything else. Just place a material, and you have to optimize the thickness and the distance and all those things and the properties of what material you will use as an interface, and you can stop the crack. So, and the effect will be different if this interlayer or one interface is at an angle. So we have done some calculation for that also, and if you change the angle, it differs a little bit, but the trend is same. So when it is going from stiffer to compliant, it is attracted by the interface, and opposite happens, it is repelled by the interface. So the crack driving force decreases when the opposite happens. So this was already done, and now let us talk a little bit about path independence. And so, as I said, if it is path independent, J-tip will be equal to J-far. If it is not, which happens in the case of what we call a material inhomogeneity. Material inhomogeneity not necessarily has to be an interface. It can be a hole, it can be a carbide, it can be anything which is deforming differently in the reference configuration. So this extra term, if it is negative, so if C inhomogeneity term is negative, that means you have less energy available than what you are supplying in terms of J-far. So crack will have a tendency not to grow as faster as it could, and the opposite will happen. So if C inhomogeneity is higher, in that case J-tip will be higher, in that case crack will have higher tendency to grow. We'll see why that happens. But before that, what we did was, there was already work done by Stefanik et al., and they did some experiment also on numerical modeling on 3-point bend specimen, and they reused different filler materials to create overmatching and undermatching zones in the well. This is not dissimilar well, but they have used different filler materials. So you have base metal, overmatching, undermatching, and then you have heat affected zone. This is interesting because all the previous studies have been done on regular interfaces. So the interfaces were very smooth, vertical or oriented. But the real interfaces are not so. They are curved. So we took that geometry and we took that information and changed it to a CT specimen of the same dimension. Why we did that? So that finite element analysis can be easier, because we don't have to model rigid pins on a 3-point bend and contact and all those things. In CT specimen, we don't put pin in the finite element analysis. We kinematically couple this hole with a reference point and apply the boundary condition on that. So this plane will be y-symmetric. And now let us come to a little bit about J integral. So if you have a conservative field, we know that if you take a line integral for the force, then if there is a source of sink of energy in terms of U, so plus minus U, it will be 0 for a closed loop. Okay, this will be the case if it is conservative, and if you have a source of, so if you don't have a source of sink of energy, then it will be 0. This idea was used by James Rice to define J integral in continuum mechanics, and to make the field conservative, he assumed the material to be nonlinear elastic. Otherwise, it will not be a conservative field. So there is a problem because real materials are not nonlinear elastic, they are elastic plastic, and the difference appears here. So when you assume the material deforms following Ramsauer-Osgood equation, and so in that case what happens, for each value of stress, you have one value of strain and vice versa. So the curve follows the same path. So here what you see is that if you go from A to B, you have some value of the integral independent of the path you take, and if you come back, it's 0. If you follow the Ramsauer-Osgood equation, the point is going to move along this line of the stress strain curve. Whether you are loading it or unloading it doesn't matter. So it doesn't feel unloading. That's not a real material, that's assumed nonlinear elastic material. The real materials deform in this way. So if you unload for the same value of stress, you will have two different values of strain. And this is not incorporated in Ramsauer-Osgood equation or deformation plasticity. So you'll have to use incremental plasticity, and then J integral is not valid. Okay, so J integral is not valid when you have unloading. This is known. Unloading happens as soon as you have crack growth, because the point which was connected in the ligament, as soon as the crack grows, that point has unloaded now. So because of that, you have unloading, you cannot avoid it. Therefore, any crack growth test, J integral is theoretically not valid. How to solve this problem? Using configurational forces. So I cannot explain the whole idea of config forces in mechanics, but the essential idea is that it's a thermodynamic force and it depends on two different configurations. So for example, if this thing is standing and if this thing is lying, both of them are lower energy state, metastable state and lowest energy state, but this will not go from here to there if I don't apply a force. This is not flat, so it will go, but if it was flat, it wouldn't. So like that bottle will not lie down. Why? Because there is a higher energy state in the path, which is this. So there is an energy barrier. So in this example, you imagine an interstitial atom which is sitting inside the material, so that is compressed by the bigger atom surrounding it, so it is not happy. If it goes to the surface, then at least half of them are gone, so a little happier situation exists. So there is an energy gradient, and because of that there will be a force which will compel this interstitial to go to the surface. Whether or not this will happen depends on the path available. So the force is there, but interstitial may not go to the surface because the microstructure will stop it because you have energy barrier in going there. So this idea of configurational forces has been applied in recrystallization, in dislocation dynamics, and recently meaning 2012 and onwards, it has been applied in fracture mechanics also. So, but it was there much before that. So this I have explained. If you have a change in material property, so whatever energy you are supplying in terms of J far, which is the boundary dotted line in the green, is not equal to the energy which is available at the tip in the contour. If you calculate J integral here, J integral there, that will not be same. So how we calculate it? We calculate it using config forces. So SLB energy momentum tensor, or also known as configurational stress tensor, is strain energy density identity matrix minus transpose of deformation gradient plus pure of stress. If you take the divergence of that, then you get bulk configurational forces, and there is a negative sign. So we calculate J integral by summing up these config forces in the direction of expected crack growth, and that makes the J integral a scalar value. If we assume the material to be non-linear elastic, so saying that this strain energy density terms includes the whole area under stress strain curve, the whole area. That means it is assuming that the material is non-linear elastic. So if we include that in phi, then whatever we do is non-linear elastic, and when we take the projection of the J integral vector in the direction of expected crack growth, we get exactly the same J integral as given by Rice. So that is equal to the conventional J integral. But that is not the truth. The truth is that plastic energy, whether it is time dependent or independent, it cannot be used for crack growth. So that cannot be a crack driving force. Only elastic energy can provide the driving force for the crack to grow. So in order to do that, we include only the elastic energy, strain energy density in phi, and we calculate F, and we sum them up, and then we project it towards the x1 direction, if that is the expected crack growth direction, so you get a scalar value of J. Otherwise, it's a vector, so you will have two components. So we incorporate this by coding it in Python or other languages, and so if you have hole like this, then you get these arrows are representing the config forces. You also have config forces at the surface because there is a transition from the material to air, and this has a dependency on the element size. So if element is distorted, so if it is not square, there is a problem. So you need to keep the elements in the square shape, and from that we calculate this. This I have explained already. And so what happens here is that you have different contours, gamma 1, gamma 2, gamma 3 at the crack tip. And as the crack moves, the contour will also move. Okay? So suppose this interface was not there, then this was a homogeneous material and everything was deforming following the same stress strain curve. So you will have same strain energy density in all the contours. So if you calculate the line integral, it will be same, so it will be path independent. But if you have an interface, then this part is deforming with a different elastic modulus, imagining that the difference is only in the elastic moduli. So this part will consume lesser strain energy density, more will be available on the left hand side, so crack will have more energy to grow. So that's the idea of attraction and repulsion because of the interface. So we took that geometry and we took the property of base metal, overmatching, undermatching and all those. And then in this case, because the interface is not perpendicular, what happens when the interface is perpendicular? The y component of j vector is cancelled out because of symmetry. So only jx is taking care of the effect which is coming because of the interface. But in this case, because it has an orientation, so you see here that the interfaces are not perpendicular. So in that case, we have to take the vector and we have to find out how much deflection it can cause in the crack because of the interface. And this scenario is complicated because we have a lot of deforming material which are deforming differently in the same case. So this is just a picture of the conflict forces which we run in finite element analysis using post-processing, and this is the plastic zone. It can be a creep zone also. So if you take a contour which is outside the deforming zone, then the elastic plastic J integral and conventional J integrals are same. So this idea can be used in creep also. We have used it. Again, day 3, you should watch that presentation. And so here on this plot, you see, and this is in the dimension. So on the x-axis is the real dimension of the specimen. And here you see different component normalized by the J far values. So you have Jx component, Jy component, and J resultant component. And from that J resultant, we have calculated how much deflection would appear as the crack approaches towards this interface. This is not a very simple scenario. It's a complicated scenario, but what you see is that the angle of deflection increases, decreases, increases, decreases. It's not, the trend is not, it increases as it comes closer to the interface from the very beginning. So that is true because crack is coming closer to the interface. But then it has a zigzag manner, and when it crosses this interface, still it has an influence because of this interface, and therefore it will drop down, and as it goes away from the influence of the interface, it will come back to 0. So it will, but this will not be the reality, because once the crack crosses the material resistance, it will start growing in that deflection direction. Okay, so that we have not considered here. For that, we will have to do damage modeling in that. So that's it. And so we conclude that. Did I finish early?
No, it's okay.
Okay. So the conclusion is that J integral theoretically, which is given by James Wright, has some problems when you have unloading and when you have non-proportional loading. So that means when you have three differently deforming materials. And the concept of configurational forces, the advantage is that it does not assume anything about the constitutive relation of the material. So it can be applied in any kind of deforming material, any kind of loading condition, so 3-point bending, tension, compression, test bend, or creep, or fatigue, or plasticity, anything, a combination of these, and it is away from any of the anomalies which is there in the theory. So theoretically, this concept is very sound. You cannot implement it experimentally, but numerically, it is very sound and it gives you a correct prediction. There has been some experimental work also by the group of Kolednik from Eric Schmidt Institute, and I cannot show those pictures, they are not there, but they have done some experiments with high carbon steel, and there is an interstitial free steel which is posed inside as an interlayer. And what do you expect that interstitial free steel should break in which fashion? In ductile fashion, right? But when you look at the fracture graph, you see cleavage fracture in interstitial free interlayer. And the crack, which was originally coming towards the interface, a new crack develops in the interstitial free steel and it joins the first one. The same phenomena we have seen in polymers also. A new crack develops and it joins the first one. So the crack is attracted so much that it doesn't wait for to go there, and maybe the resistance in the interlayer has already dropped down, so a new crack already develops there, and then these two join. So with that, I thank you very much for listening, and I would be happy to answer if I could.
So, are there any questions? Yeah.
So, Lari Rantala from PTG, the Technical Research Centre of Finland. This reminds me of an